it's Kevin and this is Chemistry Essentials. This video is on oxidation states. You'll learn what they mean and how to calculate them. Oxidation states are assigned to individual atoms in a redox reaction. These states are similar to ionic charges assigned to molecules, but oxidation states indicate where electrons are likely to be on the molecule in the reaction. To calculate an oxidation state, there is a hierarchy, or order to which you assign them. First, atoms in a free element have a state of 0. Example is silver solid or chlorine gas, which both have oxidation states of 0. Monoatomic ions gain their charge as their oxidation state. For example, chromium +4 ion gets a +4, or bromide has a -1. For metals in group 1 or 2, the oxidation state is +1 for group 1 or +2 for group 2. For example, NaCl, the sodium is in group 1, so it gets a +1 oxidation state, and the calcium is in group 2 in calcium fluoride, so it gets a +2. Next, some elements are assigned individually. So fluorine gets a -1, hydrogen gets a +1, and oxygen gets a -2, in that order going down. Then nonmetals, groups 7, 6, and 5, get their own charges. So you'll see group 7 gets a -1, group 6 is a -2, and group 5 is a -3. Then we'll see that the sum of all oxidation states in a molecule have to sum to the charge of the ion. So in H2O, it has a charge of 0. So 2 times the hydrogen oxidation state plus 1 times the oxygen oxidation state must equal 0. Then in this nitrate ion, you'll see that 1 times the nitrogen oxidation state plus 3 times the oxygen oxidation state equals the -1 charge. So our first example is potassium fluoride. The total charge of the molecule is 0. We'll see that potassium is in group 1, so it must have a +1 oxidation state by rule 3. We'll see that the potassium and the fluorine must equal 0 if you add their oxidation states together, so fluorine's charge is -1. Our next example is hydrogen peroxide. The total charge of the molecule is 0. Hydrogen gains a +1 charge by rule 4. All the hydrogens sum up to 2 for the whole molecule. And then to sum to 0 overall, you'll see that oxygen must be a -1 for each because we have 2 of them. Example 3, we have the sulfate ion. So we'll see the total charge of the molecule is a -2. The oxygen gets a -2 charge, totaling to -8 overall. The sulfur gains a +6 charge for all the charges to sum to -2 to equal the charge of the ion. Our fourth example is the acetate ion. The total charge of the molecule is -1. We can assign a +1 to hydrogen from rule 4 and sum it up to +3 because there's 3 of them. We'll assign a -2 to the oxygen from rule 4 and we'll get a -4 overall. We can add those together, we see we get -1, so carbon must have an oxidation state of 0 to retain the -1 charge overall. Looking at our fifth example, we have squaric acid. The total charge of the molecule is 0. We'll see that by rule 4, hydrogen has a +1 state and oxygen is a -2. We can calculate the totals for those by multiplying by their quantities. Then we have some basic algebra to find the charge of the carbon. So we'll have 4 carbons plus the other charges must equal 0. So we have the 4 carbons must total up to 6. And then we can do just divide by 4 on both sides and you get carbon is 3/2. You might think that's not possible, but remember oxidation states are just a guess of where electrons are likely to be in that molecule, so we're fine.